Have you ever, driven past a utility pole and really looked at it? Probably not, right?
Most people don't give them a second thought, just part of the scenery.
Exactly. But what if I told you that pole, that seemingly simple post with wires, is actually packed with some seriously specialized engineering, designed with incredible precision?
It really is. From the street, they might look pretty much the same, but get closer or look at the plans, and you see it's this complex modular system. So many variations.
So today, we're doing a deep dive into that hidden world. Specifically, we're looking at three-phase primary pole top assembly units. Our source is this really technical document. It's basically an index of drawing numbers, but with detailed descriptions for each part.
Yeah, very specific stuff.
And three-phase, just quickly, that's the standard way big amounts of power are moved around efficiently, using multiple lines for steady energy.
Right, the workhorse of the grid.
So our mission here is to kind of peel back the layers on this technical blueprint, see what surprising details pop out, and just how specialized these components really are. They're basically the backbone of our power grid.
Okay, let's dig in. So the foundation for the straight bits of the power line, the document calls them single supports on cross arms.
Right.
These are your basic units like the VC1 1X series you see listed. They're for what they call tangent sections.
Tangent meaning just straight line.
Exactly, where the line just runs straight from one pole to the next.
But what's really interesting, even with these basic ones, there are these critical differences, aren't there?
Oh, absolutely.
Like you see some labeled with an L, that means large conductors.
Yeah, and that's not just about, the wire being a bit thicker.
No, it's about the load, the weight, the tension. Imagine stringing a heavy main line, one powering a whole neighborhood, on a support meant for something lighter. That's a recipe for disaster.
Total failure waiting to happen. So these L variations, they're engineered specifically for that extra stress, that immense tension, to keep the grid safe and reliable.
And then you've got the P variations. Post insulators.
Right. Insulators are, absolutely vital. They stop the electricity going where it shouldn't, straight into the wooden pole.
Keeps everything isolated.
Precisely. And using different types, like these post insulators indicated by the P, lets engineers account for different voltage levels or maybe harsher weather conditions, things like that.
So it keeps the system stable no matter the challenge.
That's the goal.
And it's not just the main power lines getting this treatment, even the neutral line.
Yeah, the one that helps balance the load.
Even that has its own specific support. Single support, neutral on crossarm, and again, it's got its own L and P variants.
It just shows you how every single element is thought through. Nothing's left to chance.
Okay, so what about when you need more stability? Maybe bridging a longer gap between poles.
Then you move up to double supports on crossarms. Things like the VC2 series.
Double supports.
Yeah.
So literally two crossarms, or maybe two poles together.
Often two crossarms on a single pole, sometimes configurations involving two poles, yeah. It spreads the load, increases the stability, allows for maybe longer spans between poles, or sometimes specific conductor spacing requirements.
Makes sense. Distributes the weight and tension better.
Exactly.
But power lines don't just run straight forever, do they? They have to turn corners, follow roads.
Right. And the engineering changes again for that. For gentle curves, you've got units called suspension angle assemblies.
Suspension, like they let the line hang and turn smoothly?
Sort of, yeah. They manage the change in direction without putting too much sideways strain on the pole itself. Allows for that gradual curve.
Okay, but what about sharp turns?
Yeah.
Or where a line just stops?
That's where you get into dead-end assemblies. These are built to handle the full tension of the line pulling in one direction.
It's like an anchor point.
Pretty much. You have dead-end angles for those really sharp turns, and then various single dead-end and double dead-end units for when a line terminates completely.
Some of those sound pretty heavy duty, like double deadened on crossarms.
Oh, yeah. And you even see things like a feed-through guide or double dead-ends, buck arms guide.
Buck arms. What are those?
They're extra braces, basically, designed to counteract extreme tension, especially at these critical termination points. Really robust stuff.
Wow. Okay, so we've covered straight lines, curves, stops. How do they actually connect lines together or, pull power off for a street or a building?
Good question. That brings us to the junction and tap guides.
Wow.
You've got things like the three-phase junction guide that's for neatly and safely bringing multiple lines together.
Okay.
And then for drawing power off a main line, you use tap guides. There's a single-phase tap guide, maybe for a house or two, and then a three-phase horizontal tap guide for larger commercial needs, maybe.
Each one ensuring that connection is secure, reliable, safe.
Absolutely critical. Can't have loose connections or power losses there.
So really, when you step back and look at all this seemingly dry list of parts,
Mm-hmm.
it paints a picture of this incredibly detailed, meticulously engineered system. Every single component is designed for a specific job, a specific challenge in the grid.
It really does. The foresight involved is pretty amazing. From the simplest straight run to the most complex junction or termination point.
It just hammers home that the power we rely on, the stability of the grid, it isn't just luck.
Not at all. It's the result of countless, very specific, very careful engineering decisions reflected in documents just like this one.
Exactly. So maybe next time you glance up at a utility pole, you'll see more than just wood and wire. You'll see this unseen ballet of specialized engineering happening right above us.
A hidden world of complexity.
Makes you wonder, doesn't it? What other everyday things are way more complex than they seem if we just knew where to look?